So in section 3.5, we're talking about a new category of function, new type of graph, called rational functions. When we see that word rational in math, I want you to always think fraction. Rational means fraction. So 1/2 is a rational number because it's a fraction. Okay. Now 5 is also rational because it could be written as the fraction 5/1. But rational means fraction. Okay. So notice all of these functions over here, f of x, g of x, h of x, etc. They're all fractions, and there's an x in the bottom. Okay. So you could have a polynomial on top. So there could be plain numbers, or it could have an x. There's a polynomial on the bottom, including an x, and notice that that denominator, whatever you have on the bottom, the q of x, cannot be 0, because if you divide by 0, the whole thing's undefined. Okay, so let's start out. Let's graph this thing. Let's just graph just to see what it looks like. I'm going to go to alpha y equals, I'm going to graph that in there, 6 over x plus 3 times 4 minus x. I'm going to graph that, okay? And this is an interesting picture, okay? So notice that the graph is rocking and rolling, it's cruising along right here, and then all of a sudden, right here, when we get to about -3, okay, the graph zooms down. And as soon as I get past -3, the graph was zooming up, continues over here, and then as soon as I get over here to 4, on one side the graph was zooming up, and on the other side it was zooming down. Okay, so what this is saying is that this graph exists, the function exists, every single location except for -3 and +4. Now, I wonder if we could have predicted that -3 and +4 were going to be the problem areas where this graph didn't exist before we ever graphed it in our calculator. And the answer is yes, we could have known that. Remember how we said the denominator could not be 0? Because you can't divide by 0. If you want, 0 divided by 4, well, that's 0. But 4 divided by 0, can't do it. Undefined. You cannot divide by 0. Okay, back in my calculator. 0 divided by 4, 0. 4 divided by 0, error message, because you can't divide by 0. Okay? So any number, I can plug in any number I want to for x, and I can make a table. I could plug in 1 for x, or 2 for x, or -5 for x. I can put in any number I want to for x, and something will come out for y. I'll get numbers, and I can draw my graph over here. The only numbers I cannot plug in for x are values that make the denominator 0. So if x plus 3 ever equals 0, I'm going to have a problem. Okay? Well, for x plus 3 to equal 0, or some people like to write x plus 3 cannot equal 0, because if it equals 0, you got a problem. So when I subtract 3 on both sides, I get x equals -3. If I take 4 minus x equals 0, and I subtract 4 on both sides, -x is -4, divide by -1, x is 4. So the two numbers that x cannot be are -3 and +4. If x equals -3, this part will be 0, and the whole thing is dividing by 0. It does not exist. If I put in a 4 right here, 4 minus 4 is 0, and that would cause a 0 in the denominator. So x cannot be -3 or +4. Other than that, we're good. Other than that, this graph existed. It was just fine. So our domain is going to be -∞ to -3, union -3 to 4, union 4 to infinity. This graph existed from -∞ until I got to -3. -3 is where there was a problem. Then the graph resumed from -3 to +4. And then the graph had a problem at 4. And then it existed from 4 to infinity. Okay? Notice I had to put the -3 first because on the number line, -3 comes before 4. So -∞ to -3, then -3 to +4, then +4 to infinity. Okay? So that's our domain. The graph exists only in those spots. Okay. In the denominator, g of x, number 2 here. In the denominator, this graph exists, every single value for x, except for when 3x minus 1 equals 0. That's a problem. We cannot let 3x minus 1 equal 0. Add 1 to both sides. Divide by 3. 1/3 is going to be a problem area. X cannot be 1/3. 3 times 1/3. 3 times 1/3 minus 1 is going to be a 0. That will cause a 0 in the denominator, and that's a problem. If x plus 2 equals 0, we're going to have a problem. We got to say x plus 2 can't be 0, which means x can't be negative 2. Okay? So our domain, this graph, will exist everywhere except for 1/3 and negative 2. So our domain is negative infinity to negative 2. And I'm putting the negative 2 first because negative 2 is smaller than 1/3. I'm going left to right. Union, negative 2 to 1/3. Union, 1/3 to infinity. Okay? And again, you can graph that in your calculator and verify that that's what the picture looks like. Okay? You want to graph it. Oops. X times x minus 1 over 3x minus 1 times x plus 2. And sure enough, when we graph it, negative 2 is the problem. And it's kind of hard to tell that this one is at positive 1/2. I'm sorry, positive 1/3. But once you know it's 1/3, you can kind of tell. Okay? All right. Number 3. Here's our h of x function. So again, the function will exist everywhere except in places where the denominator is 0. So I'm going to take this x to the 4th plus 1, and I'm going to say, dude, you can't be 0. Okay? What numbers would cause, when would be a problem? Okay, well, if I subtract 1 from both sides, I would get negative 1. So x to the 4th can't be negative 1. And then I would take the 4th root. Problem is you can't take a 4th root of a negative number. That's undefined. So that means there's not a number that would make this equal 0. And if you think about it, you kind of already know that. If you take a number and raise it to the 4th power, it's always going to come out positive, even if you plug in a negative number. When you raise something to the 4th, it's going to come out positive. So adding 1 is still going to be positive. It's never going to equal 0. So that means this domain is negative infinity to positive infinity. And if I graph that one, and when I graph it, sure enough, this graph exists all the time. There's never a place where it doesn't exist. Okay? All right, what about number 4? Well, the only place there will be a problem in the domain is when x minus 2 equals 0. X minus 2 cannot be 0. If it ever does, we got a problem. So that means we got a problem if x is 2. If we put in 2 for x, we're going to have a 0 in the denominator. So our domain is negative infinity to 2, union 2 to infinity. 2 is the one number that x cannot be. Okay? Number 5, x squared minus 4 cannot be 0. Now, a couple ways you can solve this. Since this is a quadratic, there's going to be 2 answers. So you could solve it square roots, you could solve it with factoring. This one actually does factor to x plus 2, x minus 2. X plus 2, x minus 2 cannot equal 0. So x plus 2 can't be 0. X minus 2 can't be 0. So x cannot be negative 2, and x cannot be positive 2. We probably recognize that those are the numbers that would cause a problem. 2 squared is 4, minus 4 would cause a 0. Negative 2 squared is 4, minus 4 would cause a 0. So again, our domain is all the numbers except for 2 and negative 2. So negative infinity up to negative 2, union negative 2 to 2, union 2 to infinity. And again, you could graph that and verify that 2 and negative 2 are the one places where the graph does not exist. Okay? All right, so we're finding the domain. When we have rational functions, fraction functions, the domain is all real numbers unless there's a number that makes the denominator 0. That number would have to get kicked out of the domain. Okay? Okay. Couple of little notation things here. I think the easiest way to do this is show you an example. they're saying as x approaches certain numbers, as x approaches c, and the little plus is saying it's approaching it from the right. The little negative is saying it's approaching it from the left. If it approaches infinity, then that means as x gets larger and larger and larger on the x-axis, so 10 to 100 to 1,000 to 1,000,000, as x gets bigger and bigger, they're asking you what's happening with y, or as x approaches negative infinity. That means as you go to negative 100, negative 1,000, negative 1,000,000, what's happening as the graph goes to the left forever. Okay, so let's look at an example here. Number 6, they've given us the graph. And believe it or not, this is a good graph. You know, I don't even have to type it in, but I will just to show you that that's really what the graph looks like. X minus 1 is on top, and x minus 3 is on the bottom. And when I look at my graph, sure enough, it does look like this picture over here. Now, one thing I want to point out. On the graph they showed us on paper, they've got these little vertical dotted line right here and another little vertical dotted line right here going, I'm sorry, this one's going horizontal. A vertical one and a horizontal one. Okay, we're going to talk about these more later, but these are called asymptotes. These are imaginary lines that don't really exist, but they're just a visual to help us kind of get our picture drawn really well when we graph it on paper. Notice that your calculator does not draw the asymptotes. But look where that happens. This vertical one happens when x is 3. At x equals 3, that's where that vertical line is. So if I go over to 3 on the x-axis, that's where that little vertical line is. The horizontal one is at y equals 1. At 1 on the y-axis, that's where that little horizontal one is. Okay? All right. We'll talk later about why they occur at x equals 3 and at y equals 1, but for right now, we're just going to trust that that's a good graph, okay? All right, so this right here is saying as x approaches infinity. That means as x gets bigger and bigger and bigger. On the x-axis, as we go to 9, to 10, to 100, to 1,000, to 1,000,000, as we go further and further to the right, the y, because remember f of x is y, the y value is approaching what number? Well, as I go further and further to the right, notice that this graph seems to be leveling off. It's approaching the number 1. That's the y value that it's getting really close to. Okay? I would point out that it is approaching the number 1 from above. The graph is always higher than 1, but it's getting very close to 1. Okay? All right. As x approaches negative infinity, that means as x gets smaller and smaller and smaller, it goes further and further and further to the left, what is the y value approaching? Well, in this case, y is also approaching 1, but it's approaching it from below. This graph is below 1, and it's approaching it from underneath. Okay? Next one, as x approaches 3, and they've got a little plus sign. That plus sign means as x approaches 3 from the right. Okay? Well, here's the x value of 3 right here. As x approaches 3 from the right-hand side, notice what happens. As x gets closer and closer and closer to 3, the y value is going higher and higher and higher and higher. That means the y value is approaching infinity. On the other hand, as x approaches 3 from the left, the little negative is saying from the left. So as on the left side of 3, as x gets closer and closer and closer and closer to 3, notice that the graph is dropping. That means the y value is approaching negative infinity. Okay? All right, so that's just kind of how to interpret that. We call, like I mentioned, this little dotted line here at x equals 3, we call that a vertical asymptote. Notice how asymptote is spelled. It's only got one S, but it's got this extra P in there, which is weird. But that P is silent, so we pronounce this asymptote. Okay? Vertical asymptotes are the imaginary line that the graph gets very, very close to, but it doesn't touch. Notice that from the right, the graph approached the line, but it never touched it. It just zoomed up. From the left, the graph approached the asymptote, but it never touched it. It zoomed down. So a lot of times when you have a vertical asymptote, one side will zoom up and the other side will zoom down. Doesn't have to be that way. It's possible, we'll see some later, where both sides are zooming up or both sides are zooming down, but that's an option that one side could go up and the other could go down, okay? We'll talk more about horizontal asymptotes in a minute, but for right now, vertical asymptotes, sometimes I'll just abbreviate it VA for vertical asymptote. Vertical asymptotes typically occur when the denominator is 0. So notice this equation right here. Do you agree that 3 would be the one number they got kicked out of the domain? Because 3 is the value that would have made the denominator 0. So over here, the values that we were kicking out of our denominator, that caused our denominator to equal 0, and that's why we kicked them out of our domain, good chance that that's where these vertical asymptotes would occur. Since 3 would cause this denominator to equal 0, that's why there was a vertical asymptote there, okay? Now, there is one little exception to that, and that is something that we call a hole, okay? Holes occur when canceling occurs. So in other words, if my function f of x had had an x minus 3 in the denominator and an x minus 3 in the numerator, the x minus 3's would cancel. Okay? Now, 3 would still be kicked out of the denominator. It would still not be part of our domain. We'd still have to kick it out of the domain. But there wouldn't be a vertical asymptote at 3. There would be a hole at x equals 3. Okay? And I'll show you an example of that in just a minute. Just realize, or in the next video, just realize for right now that find out where your domain exists. Anything that gets kicked out of the domain is potentially a vertical asymptote. But if it canceled, instead of a vertical asymptote, it would be a hole at that location. And I'll give you an example of that on the next video.